T-minus 10, 9, 8, 7, 6, 5.
3, 2, Roger, 1, 0, Roger,
I feel the liftoff. The clock has started.
Space shuttle spreads its wings one final time for the start of a sentimental journey into history.
Shoulders of the space shuttle, America will continue the dream.
Well, thanks for having me today. This is quite an exciting moment. Now, you've been working on this for a long time, so see where we are.
The most exciting thing is actually that we're able to study two bacteria together, and that's very different than previous experiments that have focused on one bacteria at a time. And the reason that that's especially important is that in places like the International Space Station, when they actually sort of swab the walls or the filters, they find lots of different organisms growing together.
Really?
And when they do that, they change in ways that we can't even predict. And so a controlled experiment like this will really allow us to understand what happens when they interact with each other.
They behave differently or they grow differently in space. Is it the zero gravity or is it the human body reacting to zero gravity?
That's a really great question because that's something that we're still studying in microbiology today. And I think that the majority of the changes that we've observed so far are just because of the microgravity environment.
Wow, almost sounds like a science fiction movie.
My name is Swati Ravi. I'm a third-year Columbia College student studying physics, and I'm here in the Dietrich lab. My main role in the project is to oversee all of the lab biology work that we're doing, and so my work really focuses on understanding what kinds of conditions the bacteria will be in when they're transported to the Kennedy Space Center and also when they're transported to the space station, and understanding the ways that we can keep our samples alive and viable and our experiment interesting and scientifically relevant the whole time. We're testing things like how temperatures affect the growth and how the different media that we can grow our bacteria on affect the ways that they're growing.
This is our payload. The heart of our project is the cells, and the cells are located in 3 places in the payload. So the first place they're located are these 3 petri dishes here, and these are in a snug outer casing to keep them from moving. And these will grow basically during their time in the International Space Station, and when the cells return to Earth, these are the plates we'll use to test antibiotic resistance, and so how these cells have changed their antibiotic resistance by being in space.
We're going to be working in zero gravity condition. We can see the actuator pushes a piston inside a syringe, and that displaces the fluid into these 3 different compartments.
It only happens once at the very end of the experiment, so right before we leave the ISS, we're going to preserve the cells as they are.
So you want to tell us where we are right now?
Yeah, so we're in the machine shop right now. This is the 3 members of our Mechie team. Right now we're working on an interfacing piece to connect our payload to an exciter, and that's how we're going to test the payload to see whether it's able to withstand all these forces that it will be explode on it.
So that's cool. You want to tell people who might not know what an exciter is?
Yeah, sure. Basically, it exerts vibrational forces on the payload, and we want to see whether the payload can withstand those forces, since those are the forces it'll be subject to during launch and landing.
We're testing today, hopefully, sort of with the vibration, and yeah, I think it's. I mean, I'm very excited. No, it's going to space. It's crazy.
Max, okay, we're gonna go down here. Release this. Okay.
Let me get you. Oh, Lord, let me pull that a little bit down. All right. Mason Rhodes, show and tell. Hey, everyone. My name is Mason Rhodes, and I'm an engineer on the SPOCS team at Arkansas State University. Now, part of the roles as an engineer is to 3D model and design objects that the biologists may need. And if you follow me over here, I'll show you some of the objects that we've modeled so far. As part of the SPOCS project, NanoRax, which is a company working with us and NASA, has requested that we fit our entire project within this container. So as a mechanical engineer, we've determined that the best way to run multiple projects at the same time for testing is to 3D print copies of each box that we have so far. Along with that, we've printed off hubcaps and the circuit board that goes along with it to get the exact feel for what the box should look like, container-wise. Inside the container, we have pods, which will host the waxworms, food, and plastic, as well as cameras hosted above to make sure we get accurate pictures aboard the International Space Station. At the moment, we have multiple different designs that are currently being printed and tested to find the optimal solution for this project.
So we're seeing these waxworms in space, and we're seeing if they're able to degrade this polyethylene in our controlled environment. The biologists are working on creating a colony.
So, our NASA SPOCS lab is on the 3rd floor here at ABI, and this is where our engineers and biologists have our own space so that we can run trials, house our worm friends, and basically just make plans, talk about science, talk about NASA. For the biologists, our incubator. It looks like a gigantic refrigerator, but it's actually warm in here, and this is where our worm buddies make a nice warm home. All of our friends, especially our future astronauts, they like this space. This is where they like to stay. If you take a look on the inside, not maybe the fanciest setup we have, but we have a grid system where we organize our jars, and our worms are in those jars. They're kind of tiny, so they don't need very large homes, but I promise you that they are very happy in there. Aside from that, we have our 3D printer, which is what our engineers primarily focus on. So these guys love this thing for making prototypes, especially when dealing with us biologists, because we like to change our minds a lot. So they can print as many prototypes, as many styles, as many different materials, colors as we need, and we can test them out with our worm friends because they're finicky as well. Prototype of this guy. This is the one straight from NanoRacks. This is the one that will actually be going to space, but we don't want to perform all our very scary tests on our real one. So this is why prototyping is very important.
Ooh, okay. Here's the first piece of the box itself.
One of the greatest challenges our team has faced has been working remotely due to the pandemic.
I'm going to keep it in the paper towel for now. Or maybe not. Maybe I should open it. I can open it. Should I? Should I keep it in the paper towel or should I open it?
In fact, some of us haven't even met each other in person.
Open it.
Let's open it. I can always put it back in the paper towel.
But I feel like I know every member of our team so well because of all the time I've spent on Zoom with them. So now while we're building the payload, we're not only all over the country, but all over the world. A lot of our payload is 3D printed or laser cut, and so we're able to construct it remotely without using on-campus resources.
When you're designing a physical system, like an assembly, if you can't get your hands really into it, it can make it harder to have an intuitive understanding of what is going on. So making very heavy use of CAD assemblies, being able to spin things around, make sure everyone's on the same page, that's helped a lot.
The bovine serum albumin protein, or BSA, forms protein bridges between individual grains of silica. And so when you mix dirt or sand or regolith with a small amount of BSA, hydrate it, then dehydrate it, you get a material with about half the strength of Portland cement.
So if you need to build stuff on Mars where you need a lot of mass to provide radiation shielding, this allows you to avoid carrying all the mass from Earth. You can just bring the protein powder and then use the local dirt, and you've got radiation shielding habitats fairly cheaply.
So now that we've assembled our structure, we're going to leave this out in the elements here on Mars for minimum of 24 hours, but ideally we'll leave it until the end of our mission and break it down on the final day. Hopefully it will be exposed to high winds, extreme temperature changes, and other weather anomalies, and we'll get to see how it holds up.
At the moment, we're working on a full-sized brick making machine and an accompanying rower. We're thinking of working on, finding the best ratios of the protein to the regolith to the water, and then the best process for creating the bricks. And we're also looking into ways to recycle the material. After you melt it back down by pouring water on it, is there a way to reuse this to reduce the amount of waste?
We'll be making about 20 bricks on the International Space Station. And then instead of doing crush tests, we'll be micro CT scanning them, which will give us a 3D overview of what's going on inside the brick. Then we'll utilize citizen science and have students count the protein bridges between individual grains of silica in these bricks. The assumption being the more protein bridges, the stronger the brick.
Basically, our project will be testing non-fouling polymers in microgravity. And so these polymers have been scientifically proven on Earth to resist bacteria adhesion. So currently on the ISS, they have these different solutions that will clean high contact surface areas, door handles, counters, things like that. And so we're thinking that if you can put these non-fouling polymers on these high contact surface areas, then we can prevent bacteria growth in the first place.
So we have a few polymers that we do adherence testing for on aluminum. Our polymers of choice don't inherently stick to aluminum, and so my job is to use a silane initiator to modify the surface of our aluminum, and that helps the polymer to bind to the aluminum better.
One of the most important aspects of safety for our project is to ensure that we have 2 layers of containment for our experimental fluid. And so to model this, I've been using CAD, or computer-aided design, in order to design all of our parts to their exact dimensions and ensure that we have 2 layers of containment within to house our experimental fluid.
Basically, we have to be able to initiate a bacteria release in space without any interaction from crew. So we're using these actuators, which will extend and pull these pins like that, and that will release bacteria into the broth for our bacteria to start growing.
As you can see, an actuator pulls a pin, a spring fires it distant down, and the O-rings provide a seal. The bacteria sits in between our 2 O-rings and then is introduced into the wet space after the pin is pulled.
One of these flasks has bacteria that we put underneath the recommended storage conditions, while the other was at room temperature. We are now comparing the growth rate between the 2 different bacteria as we monitor the gas production rate using the balloons attached to the top of the flasks.
Hot liquid into a beaker.
Wow.
And then you write a paper about it.
Oh.
Yeah, and that's so cool.
And this is how you get your PhD.
My name is Sydney Rollins. I am a graduate student in the Masters in Biotechnology program here at UNH Manchester. I am one of the co-leads of Team Cook's Nomads project. I am mostly interested in microbiology in terms of research, specifically antibiotic discovery.
Hi, my name is Raymond Miller. I'm a master's candidate here at UNH Manchester. As one of Dr. Cook's senior researchers, she came to me with an opportunity she heard about for a call for proposals in a science newsletter.
And it really drew my attention because the program was specifically looking for ideas related to antibiotic resistance, combating the issue of antibiotic resistance, or sustainability of space travel and life in space. And I felt like our project was really well suited to that.
We are setting up a device, and it allows us to culture bacteria in a more in situ-like environment by actually sending up soil. That's where we're getting our bacteria from. And then we can look at how microgravity affects bacteria and how they are pressured into creating more antibiotics. That really gives us an idea of how bacteria will try to mutate as space exploration kind of continues and evolves.
Oh yes, get that good thermometer action.
A challenge we run into too. We're working with the Epstein lab at Northeastern University. So trying to communicate and work with somebody from a university in Boston during a pandemic is very difficult.
The most challenging part of the project has definitely been a lot of the testing and planning that we've done. As challenging as it has been, it's definitely been the most fun and rewarding part of it. Just trying to figure out what works, what doesn't work.
The most challenging part of working on this project has definitely been balancing it with the other things I'm trying to do. So being in the graduate program, as well as teaching, plus my own research, all on top of this project has been a real challenge at times, but it's all worth it.
The most rewarding part of this project is working as a team to produce something that is something you're proud of.
I'm excited about the actual scientific discovery, obviously, like what we might find in this process and what we might learn along the way as far as just how to do it, since what we're doing isn't something that's ever been done before. And obviously, I can't even imagine that moment when we're standing in Kennedy Space Center and they're taking our project into space.
I'm most excited about watching the launch at the Kennedy Space Center.
But then when it gets back, I just can't wait to get hands-on in the lab, spending days and nights, however many hours it takes to get some good data.
I am obviously excited about the launch in the future for this project, but I'm also excited about bringing our project to youth in the community and just the general public. I think it's going to be really cool and rewarding to bring our topics to kids in the area and just get kids as excited about science as we can.
We're here at Russell Elementary. We're visiting our citizen scientists. So we set up an experiment for the kids to run with our polymer chemistries to see how well they would resist bacteria.
We are actually working hand in hand with 2 schools near the Harlem and Manhattan communities. We are currently developing a 4 to 5 week course that will teach the students the different engineering disciplines that were involved with the project, and also on the biology side.
I can do laps.
They have a winner.
It's good. It's all good. It's all good. It's all good.
We go on to creating a prototype. Has anybody ever heard of a prototype before?
Well, on the space station, we're going to keep it in its larva state.
I love doing outreach because I feel like we are afforded so many opportunities with what we have as resources at Stanford that it's super, super important that we share those resources with people that don't have access to them in general.
How cool is this for you, for all of you, to get a chance to do this?
So the first time I really became interested in space and space travel was when I watched Apollo 13. I was really enthralled with all the scientists at NASA that basically helped astronauts get back home from a very dire situation. And on a personal note, I wanted to be those scientists because when my father was killed when I was 7, my mom had to raise both of us on her own. And watching all the scientists take care of a very dire situation, made me want to take care of my mom also in that dire situation. So that's why I pursued math and science and mechanical engineering up to this point.
So I am a proud Texan, born and raised, and when I was small, my parents took me to the Johnson Space Center in Houston, and it really inspired a love of aerospace in me. And so this project for me is really a culmination of that whole childhood love of space and continuation of that into a sort of more scientifically relevant way.
As a child, space was something that was so unattainable, so far away. Something I'd never imagined that I'd be able to, let alone work on this project or interact with an actual astronaut. Growing up, one of my idols was Kalpana Chawla, who shares the same name as I do. And, even though we had a very similar cultural background, the same name even, it was still so unattainable and so far away. So it's incredible to be able to have this opportunity to send something to space.
3, 2, 1, 0. Mission and liftoff. Godspeed, Endeavour, and Crew 2.
Copy, 1 Alpha.
Having that happen, having that actually work, designing something that we think will work on the space station without being able to meet in person is hard.
In the end, that challenge became our greatest strength.
Everyone has something unique to contribute since there are so many different our team members come from so many different majors. Everyone has something unique to offer, and that's what we really value on the team.
All of us are making a difference in the project in this positive manner, and we're all going to get something to, possibly change the world and other worlds like Mars.
It's so cool that something I'm working on is actually going to space. And I get to load my project at Kennedy Space Center and watch it launch, which is closer to space than I ever thought I would get.
Just seeing the results and the pictures come back, and then us being able to try and quantify that and writing a paper about it to try and expand our knowledge in that subject. That's just really exciting to me to be able to try and understand that better and to actually be part of the growing knowledge of science.